So again, we just looked at the definition of a derivative. We looked at the definition of a derivative at a particular value of x, and that was finding the slope of the tangent line. Another way to say that was that we were finding the instantaneous rate of change at x equals a. And then we looked at finding the derivative function of our graph or function f of x with respect to x. So anywhere that it was differentiable, we could find the derivative function and then plug in that value for x into the derivative to get what that derivative was. So that rate of change, what was happening at that particular value of x on that function. And so knowing that we're talking about the rate of change when we're talking about the derivative, without even using this derivative formula, you should be able to look at this for these examples here and tell what the derivative of the tangent line is. And so if we have f of x equals 5, what do you think that slope of the tangent line would be anywhere on that line, f of x equals 5? Or where would it be on f of x equals negative 2x? The other one is the line x equals 3 and the line y equals mx plus b. So with information that you know from your previous algebra courses and now knowing what it means to have the derivative or the slope of the tangent line, you should be able to answer all of those questions. So I'm just going to pause the video, give you a second to think about it, and then we'll come back and discuss it. Okay, so you guys are awesome. So we went through, okay, what does the graph of f of x equals 5 look like? Well, another way to say, if that was confusing you, we could say this is y equals 5. And you guys said, well, that's the graph of a horizontal line. So if we looked at this graph here, y equals 5 or f of x equals 5, and we're trying to find the slope of this line, you should remember that the slope of a horizontal line is 0. So we would say that f prime of x in this case is equal to 0. So the derivative of that function is 0. And we did that without even going through and looking at the limit, the formal definition of a derivative. We could also see this by taking 2 points. So this point here, when x is 0, y is 5, that's 1 point on that line. Any x value, so maybe x equals 1, y is 5. And if we took that slope between those two lines, but it told us not to actually calculate this, but we'll see, right? The slope of a horizontal line, change in y, your y value is 5 in both cases, all over the change in x, so 1 minus 0. So 5 minus 5 is 0, all over another number other than 0, which in this case is 1, is okay. And that gives us back 0. So looking at that, we can find the slope without even going through that formal limit definition. And just knowing that it's a line, you should know that there's the slope of a line is always constant. It's always that same value if it exists. So what about f of x equals negative 2x? Okay, so we just went through and discussed the rest of these, and we have y equals f of x equals negative 2x. Well, all of these are lines again, and so all of them have a slope if it's defined, and it would be the same value. Well, this is, and again, this is in the form of y equals mx plus b. It's just that our b value, the constant that we're adding, is 0. And it's in the form where we can tell the slope. And so our slope in here, another way to say this, f prime of x in this case is always going to equal negative 2. If we're looking at the line x equals 3, well, that graph is a vertical line through 3. And vertical lines actually don't have a slope. The slope is undefined. So f prime of x is undefined. And if you had chosen 2 points on that line and you used y sub 2 minus y sub 1 all over x sub 2 minus x sub 1, which it told us not to do, but anyways, you would have found that your y value would have given you some number other than 0 all over 0. And this is undefined. It's not okay to have 0 in the denominator. And if we had 0 in both, that was an indeterminate form that we had to manipulate. And then the last one was the line y equals mx plus b. And so y prime, and I'm going to get into going through the different notation for derivatives in a little bit, but this is another way to say the derivative of y. This is equal to the slope m. Okay, so knowing that and going through that, you should know if the rate of change of f of x is 0 when x equals a, what can be said about the tangent line of the graph of f of x at x equals a? Okay, so we're given that the slope of the line at x equals a is 0. So if we graphed the tangent line at that point x equals a, the slope would be 0. What do we know about the tangent line when the slope is 0? From above, you should know that. Exactly. So you're right. So the slope of the line, and that was coming through chat because so you wouldn't hear it, is 0. So we know the slope of the tangent line, I'm sorry, is horizontal. So the slope of the tangent line, let me restate this, equals 0, then the tangent line is a horizontal line. And we'll be in the next chapter when we're looking at graphing these functions, where a lot of times are going to look at when is that slope of our function equal to 0. And those are going to be special points because those are some values a lot of times where our graph is having a max point. So right here, if I was looking at the slope of this line right at this point, the max, that is a horizontal line and the slope is 0. Same idea, if I have a minimum point, the slope down here where we have a minimum value is also 0. And so finding when our derivative is equal to 0 is going to help us actually graph these functions without having just to go in and plot points. Okay, so I was just mentioning that there's different notation for representing the derivative. And so alternate notation here. So the typical notation that I've been using is that prime notation. So if I have f prime of x, so that notation reads f prime of x. Or another way that we could say that, the derivative of f of x. But there's another notation that's used on occasion, well, more than an occasion. You'll see it different times, different ways. So let's just cover them. So given a function y equals f of x, all the following are equivalent and represent the derivative of our function f of x with respect to x. So we were using this notation f prime of x. Well, recall when we have function notation, f of x, g of x, whatever of x, h of x, h of t, those are just another way of saying your y value. And so instead of saying that function notation prime of x, f prime of x, we can say it's y prime of x. Another notation is this df over dx. And this would read d, you basically just say the letter d f of, or dx, sorry, df dx. So up here in the numerator, that's telling you that you're taking the derivative of what function, in this case, the derivative of the function f, and the denominator tells you with what variable it was with respect to. So for instance, if I had v of t and I wanted to represent the derivative of that, there's a couple ways I can do that. I can say v prime of t. I could rewrite this as dv all over dt. So the derivative of the function v with respect, this in this example would be with respect to the variable t, not x. Then moving on, we have dy dx. Well, instead of calling our function in function notation, we're just saying y equals. That equation, that function is y equals. So the derivative of the equation y with respect to x, you might say d dx of f of x. So that's just saying the derivative of the function f of x with respect to x, and then d dx of y. So those are all same meaning, just different ways to write it. Those are all the derivative of the function of x. Those are giving us another function, the derivative function. But when we're plugging in a value at a particular value into our derivative, that's giving us the point or the slope at that value. So let me just read through. So because we also evaluate derivatives on occasion, we also need the notation to evaluating the derivative when using fractional notation. So we want to evaluate a derivative at x equals a. All the following are equivalent. So we were saying before f prime of a. So that was the derivative of our function x when x was a. If we were using y prime, we might use that vertical line and then have x equals a on the bottom. And that says we're going to take the derivative of y and then evaluate it with respect to a. Df over dx, and then dy over dx with the vertical line x equals a. Okay, so note as well, on occasion, we may even drop that x on the part of f prime of x. So you might even see f prime of x, instead of with the x in there, they might just say f prime. They mean the same exact thing. Okay, so notation wise, if you see those different notation, you should be able to recognize that it's just talking about the derivative, which function that it's talking about, and what variable it's representing. Okay, so looking at the example of a graph, you should be able to find when the derivative is less than 0, when the derivative is greater than 0, and when it's equal to 0. Next chapter, we're going to be able to, given a function, not the graph, be able to find when f prime of x is less than 0, f prime of x is greater than 0, or equal to 0. So let's again just kind of recall real quickly what the derivative is talking about. The derivative is talking about the slope, the rate of change of the function. And so if f prime of x is less than 0, then we know that the function is decreasing. And so if a function is decreasing, it's going down from left to right. If our derivative f prime of x is greater than 0, the function is increasing. And we always say left to right. We're always reading the graphs from left to right, because really, if I was going from right to left, right here, to me, that would be going uphill. But if I'm going left to right, this would be going downhill. And then we were talking about if our derivative was equal to 0, that was where we had a horizontal tangent line, or this is where we're going to have values where it's changing directions. So slope is equal to 0, and this can occur where the tangent line is horizontal. It doesn't always have to occur when you have a max or a min, but it will occur at max and mins on the graph. So now maybe knowing that, you guys would be able to go through and look at the graph and find what are the intervals, what values of x, when it says the intervals. And maybe we need to go through that a little bit for a second. So the intervals, these are just values of x. Where this occurs. And there was a difference between interval notation and inequality notation. So recall, so inequality, this is just kind of a review real quick. If I said that x was strictly less than a, those are all values starting at a but not including, and everything to the left. And so that was everything from negative infinity to infinity. I'm not to infinity in this case, a. And we put that parentheses there. So parentheses means that we did not include. Don't include. Where if I had put, let me just write this as interval notation really quick too. So if it was strictly, or if it was less than or equal to a, we would include that endpoint. And remember, to include an endpoint, we put a bracket there. So bracket means you're including. So if we had x was greater than b, we don't include b, but we're getting really, really close to b on the right-hand side. And we're going off to infinity. If x was greater than or equal to b, then we include b, so bracket b to infinity, and one more time. Or we might have a inequality that's sandwiched. So maybe we have a is less than x, which is less than or equal to b. So in this case, we're looking at all the values of x between a and b, but not including a, so we'd have a parentheses, comma, and we're including b, so we have a bracket. Okay, so that was just kind of a review really quick on interval notation and how to write it. And so here, that first piece, we're looking at values where it's less than 0. Okay, and then
Professor?
Yeah.
Can you scroll down for like a couple minutes, please? I didn't get it, write it down.
Yeah, of course. I'll just pause the video for a second while you guys get that. Okay, so it looks like you guys are getting it. And so f prime of 0 is less than 0. So you're looking at the graph and you're looking at where is this function decreasing. And so if I'm looking at it, it's going down, right? All the way until I get to here. And this is coming in forever. The thing is, I want the x values. I don't need anything to know about the y values in this case. I want all the x values where this is occurring. And so all the x values where this is occurring is coming in from negative infinity, and we're stopping when we get to -3. That's where it's changing direction. And so I'm going to write negative infinity. When you have infinity or negative infinity as part of your interval, you always have a parentheses around that part. You never use a bracket because that's never one particular number. It's going on forever in one of those directions. And so here we have negative infinity to -3. But if we look at this, notice that the graph starts to go downhill again over here. So you're just looking at where is it going down? And it stops. And we want to know where is the x value this starts at? And where is the x value this stops at? Where it's going down. And so in this case, we would put union here. Union means that's this plus this. So this set plus this set. So the set from x equals -1 all the way to the x value of 4. Then it asked us to find where's the derivative positive. And so positive, we're looking at the graph, where are we going up when we're looking at it from left to right? Well, it's going up in here and it's going up here. But we want the x values that are giving us where it's going up. So the x values would be from -3 in this case to -1. And then a union, so plus the set, we're starting when x is 4, and this is going on in this direction forever until, well, going on forever, so to infinity. So we have parentheses 4 to infinity. And then the last one, when is this equal to 0? Well, they're equal to 0 when we're changing direction. And so we want to find that x value where it's changing direction. And you know what? Well, it looks like it's still decreasing here a little bit. So in here, I would say the x values, this would be when x equals -3, comma, x equals -1, and x equals 4. So the one thing that students get tripped up on with this is that the x values, they want to sometimes put y values in this interval notation. We always, when we're using interval notation, we always use x except for one case. And that one case is when we're looking at the range. The range, remember, of a function is the y values. So if it was asking for the range in interval notation, that's the only time that those parentheses or brackets with those numbers are representing y values. Otherwise, when you're asking where is it increasing, where is it decreasing, where is our function equal to 0, derivative or function, or domain, and it says interval notation, you're always using x values. So any questions on that, what we just did? Oops.